Welcome back to the Deep Dive. Today we are exploring one of the most exciting frontiers in AI. We're looking at how to teach machines to understand space, not with just one sense, but through a kind of multisensory synergy. Really, it's about mimicking how we humans learn about the world.
That's right.
Our mission today is to dig into a research paper on a framework called Concerto. And the whole idea is that it strategically merges 2D visual features, so images with 3D point cloud data.
And the core idea, is that by forcing these two ways of seeing to communicate during training, we can unlock something richer.
A unified spatial representation that, and this is the key, fundamentally outperforms models trained on just one of those data streams alone.
And the beauty of this whole Concerto idea is that it's built on a foundation of, human cognition.
How so?
Think about how a child learns what an apple is. It's not just one thing. They see it, they touch it, they feel its weight, its geometry, its texture. It's this repetitive multisensory input that forms a single unified concept in their mind.
The concept of appleness.
Right. And the key cognitive goal that Concerto is trying to mirror is, it's about efficiency. Once you have that unified apple concept, you don't need all those senses every time.
You can just see a picture of an apple and your brain instantly recalls its likely weight, its texture, how it would feel in your hand.
You've got it. And that highlights the goal for AI here.
Yeah.
Learning representations that are modality agnostic, meaning they're unified and predictive no matter which sensor gives you the input.
And that human inspiration is so important because it really shines a light on a big inefficiency in our current, even our state-of-the-art AI systems. I mean, we have these fantastic single modality models. You've got Dino V2 for 2D images, and it's amazing. And then there's SOTA for 3D point clouds.
Both top of their class. But when you look at the features they learn, you find something interesting. They capture complementary information.
Not redundant.
Not redundant. One knows things the other doesn't.
Which, immediately makes you ask the question. If they're complementary, why go through all the trouble of this complex joint training? Why not just train them separately, take the features at the end, and just concatenate them?
Just glue them together.
Right. And the sources show that researchers did try that. They took features from Dino V2 and SOTA, fused them, and ran them on a benchmark like ScanNet. And performance did improve over using just one model alone.
And that result was the hint. But it was also the challenge. The improvement showed there was a richer feature space out there somewhere, but the real question was whether you could build a superior representation, not just an additive one.
So concatenation is like taping two different books together.
While joint learning, like Concerto, forces the information to be cross-referenced, synthesized, into a single unified encyclopedia.
Okay, so let's get into the architecture. How does Concerto actually achieve that synthesis? It's a two-pronged approach, right?
It is. The first component is called intra-modal self-distillation, and this part focuses only on the 3D side of the equation, building on that SOTA framework we mentioned.
So it's about making the 3D understanding better on its own first.
On its own first, yeah. It uses a point transformer V3 model in a teacher-student setup. Its main job is to get consistency across different heavily augmented 3D views.
Why is that step so important? I mean, why the teacher-student thing? We hear a lot about the unique challenges of 3D data.
We do, and that's because the 3D world has this unique problem called the geometric shortcut.
The geometric shortcut.
In sparse point clouds, the kind of data you get from LiDAR or depth sensors, it's very easy for a model to cheat. It can get high performance by just focusing on local geometric features like edges and corners.
So it learns to recognize a table just because it sees a flat surface with 4 legs, but it doesn't really understand table?
It doesn't understand that the table is made of wood or that it's in a kitchen. It learns the shape, but it misses the whole semantic context. This self-distillation step mitigates that shortcut. It forces the model to learn representations that are robust because they have to be consistent across all these different views.
Okay, so you build a solid 3D foundation that isn't easily fooled by just geometry, and then you bring in the images.
Then you bring in the rich semantics of the images. And that brings us to the second, and really the novel part, cross-modal joint embedding prediction. This is the synergy engine.
This is where the magic happens.
This is where the alignment happens. This component aligns those improved 3D point features with the corresponding 2D image patch features. And it uses something called the Joint Embedding Predictive Architecture, or JEPA.
Which is a big deal because JEPA is different from the older contrastive learning methods we hear about so often.
It's very different. Standard contrastive methods, they try to pull similar things together and push dissimilar things apart. JPA is non-contrastive. It's predictive.
So what's it predicting, if it's not just comparing things?
In Concerto's case, it's training the 3D encoder to predict the embedding of the corresponding 2D pixel features. It's essentially training the 3D model to explain the 2D world.
That makes the connection so much more active, more demanding. It's not just comparing, it's inferring. And I assume the camera data is what makes that precise alignment possible.
Absolutely. The model has to predict 3D point cloud embeddings that match pixel embeddings from this is critical, a frozen image encoder like DynoV2. The camera parameters, the intrinsic and extrinsic matrices, give it the geometric map to connect a specific 3D point to a specific 2D pixel.
And the genius of freezing the 2D encoder is that you're forcing the 3D model to do all the work. It has to stretch its own capacity, go beyond what 3D data alone could ever teach it, to successfully predict that rich 2D information.
In this combination, it yields quantifiable superior synergy. Let's look at the numbers, specifically from linear probing on the ScanNet benchmark.
Okay, give us the numbers, but more importantly, the comparison that really proves the synergy works.
So Concerto hit 77.32% mean intersection over union, or mIoU. That's a huge jump over the best standalone 3D model SOTA, which was at 72.52%.
That's almost a 5% improvement. That's massive in this space.
It's enormous. But now for the core question you asked earlier, how did it do against just gluing the features together?
The simple concatenation solution.
That simple concatenation of SOTA and DynoV2 reached 75.91% IOU. So Concerto, the jointly trained model, beat that by over a full percentage point.
And that is the crucial finding.
That's the one. It demonstrates that the joint learning process created something genuinely new, something emergent. It's not just additive blending.
That 1.4% margin is the whole conceptual victory right there. Show the 3D encoder learned a new layer of abstraction it couldn't get to otherwise.
You've got it. And when you go beyond just linear probing to full fine-tuning, the results are even better. Concerto sets new state-of-the-art results, hitting 80.7% IOU on ScanNet semantic segmentation.
What did the visualizations show? I mean, for those of us listening, can you paint a picture of why these features are actually better?
Yeah, the paper has a great visualization, figure 1. It uses PCA coloring. And what you see is that the standalone DynoV2 features, they're rich in texture, you can see the paint on the wall, but they're geometrically confused. They don't get the 3D structure. SOTA, the 3D model, gets the geometry perfectly, but it struggles with fine textures. The wall is just a flat plane. But the Concerto visualization, it has both. It marries the best of both worlds into this single, cohesive representation that has both geometric and semantic consistency.
Let's shift gears a bit to the practical side.
Yeah.
This kind of multimodal training, it usually requires tons of perfectly paired data, which is expensive. Was Concerto data efficient?
Remarkably so. The ablation studies looked at this, and they found that even when using only 20% of the available paired image data, the model still got significant improvements over the 3D-only baseline.
So the benefit isn't just about volume.
It's not about volume, it's about the quality of that cross-modal training task.
And there was another finding that felt a bit counterintuitive, something about the number of visible points used during training.
Yes, this part is fascinating. They found that using fewer matched pixel point pairs, making the task harder for the model, actually led to better performance in some cases.
How does that work?
The hypothesis is that when you hide some of the direct one-to-one connections, you force the model to predict the surrounding context. It has to dig deeper into the semantics to bridge those gaps, kind of like how we have to infer what an object looks like when it's partially hidden from view.
And all this robustness leads to some really interesting extensions, like for video, right?
It does. There's a Concerto variant designed for video-lifted point clouds. It uses reconstruction techniques to generate dense 3D data from video, which means you can apply this not just to static scenes, but to dynamic ones. That's huge for real-time applications.
And the final piece of the puzzle, connecting these powerful representations to human language. Did they manage to bridge that gap?
They did, and in a very elegant way. They trained a simple linear translator that maps the unified Concerto features into CLIP's language space.
Just a simple projection.
Just a simple projection. And that alignment immediately enabled zero-shot language probing. They achieved 44.56% IOU on ScanNet zero-shot segmentation. This is a huge first step toward true open-world perception, where you could just tell an AI, segment all the chairs, without it ever being trained on a chair category.
Circling back to efficiency for a second, what about in really low data situations?
This is where the learned features really shine. In an extreme case with only 1% of scenes available for fine-tuning, just doing linear probing with the frozen Concerto features actually outperformed full fine-tuning on the baseline models.
So the pre-trained representation is just that good.
It's that generalizable. And for a little extra performance, using something like lower for parameter-efficient fine-tuning gives you a big boost with minimal extra cost.
So to wrap up the core breakthrough here, Concerto successfully uses this idea of multisensory learning to build a unified 2D-3D representation. And it proves, with numbers, that forcing these two modalities to synthesize information creates a superior map of reality. It's richer, more robust, and more efficient than just adding two separate systems together.
And that leads us to the big provocative question for the future. The frontier this research really opens up.
Go on.
Throughout this whole process, the 2D image encoder was kept frozen. It was treated as a static source of truth. So if this joint learning is so powerful when one side is static,
What happens if you unfreeze both?
what revolutionary progress could be made if both the image and the point cloud encoders were allowed to learn and adapt together during pre-training?
Allowing them to mutually enhance one another, to forge an even deeper, more fundamental shared concept of the world.
That's it. That kind of native, reciprocal, multimodal learning, that's a critical challenge worth exploring next.
A truly compelling trajectory for the future of spatial AI. Thank you for joining us on this deep dive.